Let's now turn to two different extreme ends of early type galaxy properties. One is the supermassive black holes in their nuclei, and the other one is the dwarf family of galaxies. As it turns out, supermassive black holes, measured in millions or billions of solar masses or even more, are ubiquitous. They're present in essentially every galaxy of substantial size near us. In most cases, they don't do very much. But sometimes they accrete material from outside, and that causes bursts of great luminosity and activity. Those are the active galactic nuclei, which we will discuss in more detail later in class. The supermassive black hole paradigm for active galactic nuclei, quasars and such is now very well established. And it's interesting to figure out where did those supermassive black holes come from. If they're not doing anything very special, being X-ray sources or radio or something, one thing that we can do is probe their masses using stars as test particles. We can do this by measuring kinematics of stars in the very centers of early type galaxies. When this was done for the Milky Way, we found out that there was a 3 or 4 million solar mass black hole there, which is not very active, it just sputters occasionally. But it could have been a luminous active nucleus in the past. And as it turns out, masses of these large black holes in cores of ellipticals, or in fact all galaxies, correlate remarkably well with a whole number of other properties of galaxies, and that is telling us something about formative and evolutionary mechanisms. We now in fact think about co-evolution of galaxies and their supermassive black holes. So here is one of the first cases, the small elliptical satellite of Andromeda, M32. And what's shown on the right is profile of its velocity dispersion. You can see there is a sharp spike right in the middle, which is what you'd expect if you were to embed a large point mass, like a black hole, in an otherwise normal galactic core. This was measured for many, many more galaxies, and several interesting trends were found. The first one was that the mass of the black hole is proportional to the total stellar mass of the host galaxy, amounting to something like 0.1%. That alone suggests that there is some sort of common formative mechanism. A more interesting correlation is between mass of the black hole and the velocity dispersion of its host galaxy measured at large radii, where the dynamical influence of black hole is completely negligible. So somehow, properties of galaxies on scales of kiloparsecs are related to the black holes in their cores, which are microparsecs. There is something that couples them through 9 orders of magnitude in size. Another approach to this is by considering all of the quasar light ever emitted. We have now reasonably good understanding of the evolution of active galaxy population as a function of time, and we can assume certain efficiency of accretion, say that maybe 10% of all matter that falls into black holes is converted into luminous output. We can discuss that later. And then simply add up how much mass should have been accumulated through the history of the universe. And if we do this, we find out that on average, you expect that typical luminous galaxy today would have about 10 million solar mass black hole in its core. And Milky Way has a 3 or 4 million solar mass one, so that's perfectly sensible. The Andromeda one is maybe a little more massive. So this can be compared directly to the measurements from kinematics and census of supermassive black holes in galaxies, and we find out that two agree very well, and they correspond to the local average black hole density of about 500,000 solar masses per cubic megaparsec, which is about 3 orders of magnitude less than mass density of stars. An even more interesting relation was found by Laura Ferrarese and collaborators, and she estimated masses of dark halos of galaxies from their kinematics, and it turns out that those are correlated with supermassive black holes as well, superbly well. But interestingly, in a nonlinear fashion. whereas the masses of black holes were proportional directly to the luminous stellar mass, or at least for the bulge component. Here we find out that they're proportional to a steeper power of halo mass, meaning that more massive halos, more massive galaxies, therefore, are more efficient in making black holes. You could understand that by the more massive ones being more efficient in attracting merging fuel, and maybe that's what's going on. But what's remarkable about these relations is that they have such a small scatter. We think that merging is a fairly random stochastic process. Efficiency will vary, and yet somehow, after Hubble time or so, there is remarkably sharp correlations. So we can qualitatively understand where they come from, but their quantitative understanding, why they're so sharp, is still a mystery. And here they are, all on the same plot. The top left is proportion between black hole mass and the luminous stellar mass. Then there is proportion between black hole mass and velocity dispersion, which looks a little bit like Tully-Fisher or Faber-Jackson relation, against circular velocity, and against the halo mass, proportional to the halo mass to roughly 1.6 power. And now for something entirely different, dwarf galaxies. In Hubble's days, and for some time after, people thought there is one kind of thing called dwarf ellipticals, and they're just small ellipticals. Now we know this is not the case. There are a very different family of objects, and in fact, there may be two different families of objects, in addition to simple division of being gas-poor or gas-rich and making stars. The reason why we think they're very different is that they follow very different correlations between their fundamental properties, which I'll show you in a moment. And if those correlations are product of formative evolutionary processes for galaxies, then that suggests that they're two different paths and therefore two different families. As it turns out, dwarf galaxies, dwarf spheroidals in particular, are totally dark matter dominated. They have higher mass-to-light ratios than any other galaxies, and we think we understand why this is. Again, remembering the scenario where supernova explosions can expel gas from galaxies, they can do so in shallow potential wells, thus removing baryons. But supernova shocks would not affect dark matter at all, and so dark matter will stay. So lower luminosity galaxies will be more efficient in losing their luminous mass while retaining the dark matter, and therefore you expect them to be more dark matter dominated, which is exactly what's observed. So here is a set of correlations produced by John Cormindy that shows some properties of elliptical galaxies, dwarf spheroidals, and globular clusters, which really don't belong in this diagram at all, but they're there just for symmetry's sake, as old stellar systems. And they show central surface brightness versus radius in the top left, the central surface brightness versus luminosity in top right, the velocity dispersion versus radius in the lower left, and velocity dispersion versus luminosity on the lower right. The two families with thicker symbols are elliptical galaxies and dwarf ellipticals, or dwarf spheroidals. Little dots are globular clusters. And you can see that obviously they separate very cleanly in this parameter space. So let's look at this in a little more detail. This is just a plot of mean surface brightness with ineffective radius versus luminosity. And whereas for normal ellipticals, which is the upper right set with the red line going through them, there is a trend that the more luminous ones have lower surface brightness because they have more diffuse surface brightness profiles. The exact opposite trend happens for the dwarf galaxies. Not only is the trend opposite, but the intercept is different as well. So in the region where they overlap, the difference, or rather the ratio between surface brightness at the given luminosity implies the ratio of three-dimensional luminosity densities by about a factor of 1,000 or more, which is like between uranium and air. So these are not dwarf ellipticals. They're a different kind of thing. It's just like calling cotton puffs dwarf cannonballs. And here is a really telling diagram of mass to light ratio versus luminosity. I did not plot globular clusters and ellipticals, normal ellipticals as individual points, just indicated where are they in this diagram. And I plot the dwarf spheroidals as solid dots and dwarf ellipticals, like those around Andromeda, as the open symbols. And you can see that there is this branch of dwarf spheroidals that just shoots up, reaching mass to light ratios of the order of 100 at very low mass end. This has been confirmed by many, many subsequent observations. Now we know many more of these galaxies. This will lead into the next discussion about how we can use scaling relations and correlations for galaxy families to learn something about their internal physics and formation.